Hello everyone. So today we are going to continue our discussion with the next topic, that is nothing but the combination of resistances. So in the last class we have learned about Ohm's law, right? And we have learned about what is resistance and how, on what factor this resistance depends. Now we are going to consider different combination of resistances. See, it is not necessary that you are having a single resistor. Uh, a single resistor resistance is also referred to as resistor also, it is the same thing. So it is not possible always that you are having only this kind of a circuit, right? You have different appliances, right? Sometimes it may happen that there are different value of resistors. Let us say different kind of loads are there. Each type of appliance can have different resistances, right? So let us say these are three different resistors, right? R1, R2, R3, there are different value of resistors, and it is possible that I can connect these combination of these in an electric circuit. So one of the combination is nothing but series combination, right? And second combination is parallel. So these are the two major combination of resistances in which they can be connected. So these combinations will govern these combinations are decided on the basis of values of current and this potential difference across each resistor. So in the way you are connecting these resistors, they will direct how the currents and voltages are going to be around that resistor. So that combination is series and parallel. So we will be studying them one by one. So let us first see the case of a series combination, right? So for a series combination, again, I will be considering, let us say these were my three resistors, and I will mark the terminals of these three resistors, right? Let us say this is first and second terminal. These are the terminals of the resistor, right? So that I can explain you how I am going to connect this, right? Now what happens? Suppose the connection pattern of this is going to be like this, right? The ending terminal of your one resistor, right? The ending terminal must be connected to starting terminal of the other, right? So this is a general feature of connection in this case of series combination. What I mean is that suppose I am going to connect them in series, then what I should do is this second terminal must be connected to the third. That is the ending terminal of this first resistor is connected to the starting terminal of the R2 resistor. And again in this case the ending terminal of this connected to the first. And I am now left with this series combination. That is, now the circuit becomes like this, or now the combination will become like this, right? So this is how this is your first terminal and this is your sixth terminal. So now you have a combination like this, and after this, across the first and the last terminal of this combination, suppose I apply a potential difference through a battery. That is the value of this is V volts. Now this combination, now this your combination is called a series combination. Now suppose I consider the current in this case is I. So I told you that flowing of current requires two conditions. One is the presence of a potential difference, which is here. And the second condition I told you is that there must be a closed path for current to flow. So you can see that the current has only this one path or only a one loop to flow, that is this loop. So the current will pass here, or you can see that if you have only, suppose there are A and B stations. So if there is only one road connecting these, you have only, your vehicles can go only on this road. Suppose there are so many roads to go from A to B, then you have so many options to go from A to B via different routes. So that is the same case with the current. So the current has only one highway to flow, right? The vehicle has only one highway to go. So the current won't be going anywhere other than this path. So so that is why these resistance are connected like this, and one by one this current will be, first the vehicle will appear here, the same vehicle will appear here, and all, suppose 10 vehicles are going from coming from here, so all the 10 vehicles will be passing through all these three resistors. So that is the case. So what I mean is that if you find the value of current across each resistor, it is going to be same. So current, let us say the current flowing in this R1 is I1, right? Here it is I2 in R2, and here it is I3. So what I mean is that the same I will flow here, the same I will flow here, the same I will return to this negative terminal. So I am telling that I1 is equals to I2 is equals to I3 is equals to. So now you can see that this is an important feature of this series combination, that the current across each resistor is same. That is the, so this is a strong distinguishing feature when you are trying to point out whether the, because there will be numericals and there are situations when you need to find it, identify which combination it is. So you need to check for the current in some cases, and you will see that current across each resistor is same in series combination, right? So this is the case of a series combination. You will check and find that. How will you find? Suppose I will connect an ammeter everywhere. I will ammeter. I told you we mark this ammeter like this, and it is always connected in series. Series, why series? Because current is if you are trying to find a current across each element, then the current which flows through that element is going to pass through the next stage. Like suppose I connect an ammeter here, so this ammeter will read value I. Suppose I connect an ammeter here, this also will read a value of I. Everywhere if I connect, everywhere the current will be I. Now from Ohm's law, what you know this at, from Ohm's law you know that V is equals to IR. So that will be valid everywhere, right? Here also. So I can say that suppose the value of voltage difference is V1 across this resistor, right? And V2 across this resistor and V3 across this resistor. So I can write that V1 is equals to I1 R1, which is nothing but I R1, because I1, I2, I3 and I1 is same. Similarly V2, let me write it as with proper subscript, right? Okay, that is fine. I have considered V1, V2, V3 only, that is fine. So V1, V2 is what? I2 R2, and it is nothing but I R2. And V3 is what? I3 R3, which is nothing but equal to IR. So from these three, you can see that, and from this also, whatever potential difference you are going to apply, it is going to be seen across all the resistors with a different value. What I mean is that this total potential difference V is nothing but equal to sum of these individual potential differences across each resistor. That is, if I try to connect a voltmeter across this, right, a voltmeter across this, a voltmeter across this, so they will read the readings of V1, V2 and V3, and if I sum these three, if I sum these three reading, what will be happening? It will be equal to the total potential difference applied. So this is actually a law also, which is also referred to as the Kirchhoff's voltage law. Right. Kirchhoff's voltage law, rather it is not mentioned in your textbook, but it's better to know right now. Kirchhoff's voltage law states that across the closed path, right? Since I am having a closed path, if I begin from this point, I can reach continuously. There is a loop there going on, and in a loop, the total voltage law, the Kirchhoff voltage law says that the sum of all the voltages applied is equal to all the voltage drops across the each resistor, which is the case here. So this is nothing but a Kirchhoff's voltage law. So in your textbook, it is mentioned that if you connect voltmeter across each of the resistor and sum these, you will get it equal to this total voltage drop, or the total voltage of the battery which you supplied to this circuit. So that is nothing but a verification of Kirchhoff's voltage law only. Right, now I can expand this particular thing by Ohm's law. So you can write V nothing but it is equal to I into, let us say, R equivalent. So what will be my objective is now I'm going to convert all these three resistors into a single resistor. That is the simplest circuit I want. This circuit, my idea will be to reduce all of the circuits into the simplest form where there is one single equivalent resistance, a voltage source, and a current. So this will be my ideal circuit which I want to this particular circuit to reduce into. So for that I am making this analysis so that this combination of circuit reduces into a much simpler form so that I can analyze it easily. Okay. Rather, this is a very simpler series combination. There can be combination of rather both these combinations, series and parallel combined in a single circuit that we will be seeing. So IR equivalent, you can see that V1 if I replace by this is IR1. Similarly, V2 is IR2. Similarly, V3 is IR3. Now, if I can take out this I common from all of these, I can write R1 plus R2 plus R3. And if I cancel these the I are reduced to this expression that this particular expression. So this is nothing but your expression for series combination of resistances. That is, if three resistances or n number of resistances are connected in series, then there is equivalent is the thing, but it is the sum of all the resistance. That is R equivalent. Suppose n resistances are connected in series, then it is nothing but the sum up to the nth resistor. And what is typical about this connection is that current across each resistor is going to be the same, which is in this case, right? But you can see that the voltage differences across each of the, that is the potential differences across each of the resistors is going to be the difference. So this is a strong indicator which will tell you that whether it is a series combination or whether it is a parallel combination, right? So this is about a series combination. Okay, so you can see that the current is same across all of the branches. So now let us move to the second type of categorization of combination of resistor, which is nothing but your parallel combination. And in this, what we are going to see is that the opposite of the series combination is going to be happen. So how, let us consider the same case again, right? Suppose again I have these three resistors, right? And again I have these terminals. I am naming these terminals. First time I am now, for this first and the last time I will be mentioning the terminals like this so that you can understand the combination. So what will be my uh, uh, criteria for parallel combination is that all starting and ending terminals are you can say all starting and ending terminals are the same. That is starting terminals and ending terminals are going to be connected like this. Suppose this is the R1 resistor. So I am going to connect R1 like this, right? I can write like this. This was the first terminal of R1 and this is the second terminal. Similarly, I am going to connect the R2 also, which is having the same starting terminal, which was 3 and it is 4 here, and this is going to be your R. Similarly, R3 also I am going to connect like this. Here your fifth terminal was this one. This is all the same terminals are there, the sixth one. So you get the idea that all of these are connected in this way, that there is only a one starting point and one ending point. So this combination is going to be called as parallel combination. And now when you are going to apply a potential difference across this combination, right, like this, let us say this is V, and now the current flowing here is I. So this type of combination where you can see is called as parallel combination. Now you can see, I told you from the example that from A to B, if you have three different paths, then vehicles can go from three different routes. The same is the criteria for current now. Suppose this I current was flowing, and if it comes here, right, till here it is I, and now it can see three different highways, right? These different, so many vehicles are, suppose 10 vehicles are here, so many different highways are here. So vehicles can go in different highways. Suppose the road conditions are best in R1. Suppose there is a very good condition, road condition is there in this particular path, then more vehicle will be going through this. Meaning is that if resistance is going to be high, less current will flow in that particular path. So please understand this from right here only, that the most resistance path is going to be the less current, as we know that simply R is equals to V by I. So if resistance is, you can see from this relation that the resistance is inversely proportional to the, you can see what is current. So if resistance is inversely proportional to the current, so the current will be following the least minimum path of resistance. That is, more of the vehicles. Suppose number of vehicles is your current, and these different loops, because there are too many. The one loop is here, the second loop is here, the third loop is here. So many paths are here for current to flow, right? So these many paths, there is these many types, these many possibilities are there, a value of current to flow. So what will happen? I1 current, let us say that it is flowing here, I2 is flowing here, I3 is, right. So this is now the criteria. One thing I want to point here is that now in this case, I told you that what is potential difference. I told that we are considering potential difference at 2 points, right? Potential difference is a property which is considered on the basis of points in a in electric field, or the point in the presence where current is flowing actually. So at this junction point, you can see that these starting and ending points of all these resistances or resistors is same. So whatever the potential difference is here, let us say the potential at this point, the electric potential at this point is V1, and this point is same for all of these, right? So V1 is the potential, electric potential of R1 at this starting point, R2 also, R3 also. And suppose V2 is the electric potential at this point, and this is same for all of the resistor. So suppose V1 minus V2 if I'm going to do, so it will result in V only, because these points are same for all and electric potential is measured on the different points, if the value is different. If the points are same, the potential is going to be the same. So the points are same for all of the resistors. So if I find the difference, which is the electric potential difference, so if I find everywhere, it will be V. So the meaning is that in parallel combination, I can see that what is going to happen. If I take a voltmeter here, because there is a criteria for voltmeter also, it is connected in parallel, that is across each resistor you are going to tap in the voltmeter and you are going to check the readings. So for this also you will tap in the voltmeter here, R1 let us say, right? And for this R2 also, for R3 also, you will be going to uh, put the voltmeter in the same place. So what will happen, you can see that it will result in nothing but the same reading across all the cases. That is, V1 is equals to V2 is equals to V3 is equals to, because the starting and ending points of all are same. So between these points, if you find the potential differences, the points are same, the potential difference is going to be the same, right? Since the potential difference is going to be the same, now the current will heavily rely on nothing but these resistances, right? The more the resistance in a path, the less the current in that path will be, right? Because current is inversely proportional to the resistance if the voltage is kept constant. So the voltage is constant in this case now. So you can see that similar to the previous case where I told you about Kirchhoff's voltage law. So here is a concept of nothing but called as Kirchhoff's current law, right? Abbreviated sometimes at KCL also, and KVL we call Kirchhoff's voltage law, we call as KVL. So experimentally now there are different paths. So now suppose you connect an ammeter here, 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 which is measuring current. So what you will observe that the reading in this A1, this reading and this reading, if you sum of all of these, it will be equal to the total current, which is nothing but your Kirchhoff's current law. That is the total current I, which is entering before this combination, right? Which is nothing but equal to I1 plus I2 plus I3. This is nothing but your Kirchhoff's current law. That is, at a point, the total current entering is the total current exiting the point. So the entering current is I and the exiting current is I1, I2 and I3 together. So these both are going to be equal. That is the number of vehicle. Suppose here are 10 number of vehicles. So all of them will reach here, right? This will finally all of these. Suppose 2 went from here, 4 went from here, and 4 went from here. So 2 plus 4 is nothing but 10 again. So it will be all of the vehicles will be meeting at this point again. That is compulsorily going to be happen. It is a law. It will be followed. So now if I see the KVL, sorry, the Ohm's law, it is nothing but V equal to IR, or I can write from here I is equals to V by R, right? So I can write this V as nothing but I as nothing but V upon R equivalent. So now again my idea will be to combine all these resistance into a single resistance, that is R equivalent. So if I am going to do this, I can replace VI by, let us say, total potential difference which I applied to this battery upon R equivalent. And I1 is going to be what? It is nothing but the voltage across this resistance, across the resistance of this particular branch. So it is R1. So what will be I1? It will be V1 by R1 plus V2 by R2 plus V3 by R3. But since you know this, so from 1, if I use one equation, I can write that V by R equivalent is nothing but V1 is nothing but V only, V2 is V only, and V3 is V only. So I can cancel these V from the numerator part. So I can write that 1 upon R equivalent is nothing but 1 by R1 plus 1 by R2 plus 1 by. So this is the formula for a parallel combination of the equivalent resistances. Of course, you can solve this and you have to reciprocate it to find the value of the R equivalent resistance. So this is the formula for the parallel combination of resistor, which you should remember. That is, if the voltage, this is the important criteria, right? Okay, I can also write it here. Let me write, or better, you can remember that voltage or the potential difference across each of the resistor should be same, right? So this is the criteria to identify also. That is the uh, let me mark it, the potential difference, right? Potential difference across each resistor is same. That is the thing. This have we used, and then we put the Kirchhoff's current law. This is also not mentioned in your textbook, but they have placed an activity in this case. They have just realized this Kirchhoff's law through an activity, so that you can know that incoming current is equal to the outgoing current at a node or a junction point, that is we call, because so many branches are meeting and going out. So this is the formula which you need to remember, the equivalent resistance formula for a resistance, for a parallel combination of resistance and a series combination of resistance. Right. So this is about the parallel combination. So typically there are some questions which are asked based on this combination of resistors. So let us consider some questions. Suppose I have a branch of resistor, let us say like this, it is connected. Three branches. And let us say that the voltage applied here to a battery is, let us say, 20 volts, and this is nothing but your 2 ohms, this is nothing but your 5 ohms, and this is nothing but your 10 ohms. So suppose they are going to ask you, let us say you want to find current in this particular That is the total current. So we know that current is nothing but V by R. So we know from here, and R I need to find for this combination, which is nothing but your R equivalent. So I know that this is nothing but a parallel combination. You can see that. Okay. So parallel combination means what? So 1 by R equivalent is nothing but your 1 by 10 plus 1 by 5 plus 1 by. So if I am going to solve this, right? So let us solve this. So this will be 5. If you are going to solve this, so it will be, let us say, 5 plus 10 by 50 plus half. In the simplest manner, I am going to solve this. So this is nothing but 15 by 50 plus half, or you can say that 30 plus 50 upon 100, and this is nothing but 80 by 100, which is, if you simplify, this is nothing but 1 by R equivalent, right? And it is going to be 4 by 5, or not 4 by 5 ohms, rather it is 1 by R. So R equivalent is nothing but, you will reciprocal this, so it will be 5 by 4 ohms. So you know the value of equivalent resistance, right? And now I can use this particular formula to find current, which is, because now what happened? Now what happened? This circuit has now reduced into this form. This combination is now reduced to this R equivalent. That is this combination. This whole of the combination is now replaced by a singular R equivalent resistance. So I am replacing this by this. This is 20 volts and this is going to be I. So you know that R equivalent is nothing but 20 upon I, which is 20 upon, sorry, I have written this wrong. So you can write that I is nothing but 20 upon R equivalent. So you have found the value of R equivalent, which is 5 by 4. So this is nothing but 20 into 4 by 5, which is 16 amperes. So that means 16 amperes is the total current which will be going here. So this is the solution for this particular question, that is a 16 ampere current is flowing in this case. Now let me elaborate this discussion a bit to tell you that how, let us say, the current is going to be divided across the each of the resistors, because that is the effect I want to consider, right? To tell you that how the resistance is inversely proportional to the current. Now you know that 16 ampere was the current. We found it as 16 ampere current is totally entering in this. Now across is this 10 ohm resistor, the voltage is also V1 by R1 will be the current I1. So V1 for all the voltages is going to be the same, because this is a parallel combination. So V is nothing but 20 and R1, you know, it is going to be 2 amperes current, that is I1. Similarly, if you are going to find the value of I2, it will be total voltage upon this resistance, which is 20 by 5. It is going to be 4 ampere. This is your I2. I3 is going to be what? 20 by 20 by, which is going to be 10 amperes. This is your I. Now observe this. First of all, can you see that I1 plus I2 plus I3 is what? 2 plus 4 plus 10, which is coming out to be 16 ampere, and which is equals to I. Okay, fine. Kirchhoff law is verified. But now you see the division of the current. Can you see the division of current? See, it is 2 ampere I1. Here it is 2 ampere. Let me mark it with a different color rather. So in this it is 2 ampere. Here it is 4 ampere. Here it is 10 ampere. In which case you are finding the maximum current. So the current is maximum in this particular case. See the value of resistance, it is minimum. So 2 ohm is the minimum resistance, the value of current is the highest there, which is 10 ampere. And when the current and the resistance is maximum, the current value is the minimum, which is 2 ampere, and 5 ohm is the middle one. So you can see the value of current there is in between the two, that is 4 ampere. So you can see that here you can see your I is inversely proportional to R, or R is inversely proportional to R relation. Right. So this is how you can see that the division of current is taking place across each of the uh, resistors. So when the voltage is kept constant, same across all the resistors, the current will be divided according to the value of resistance, right? That is the beauty of this. That is how the current is going to divide. You can easily see, right? So this is how we analyze this circuit. And suppose one more thing I need to point here is that let us consider this case, right? You can see what is the value of equivalent resistance we got. R equivalent, you got it as what? We got it as, I think, 5 by 4, right? Yes, 5 by 4 ohms, which is what, around 1.25 ohms, right? See the value of this resistance. What is the minimum value of this in this combination? 2 ohm is the least value of resistance. The least resistance is 2 ohms. And what is the equivalent resistance you got? 1.25 ohms. So R equivalent you got is it as 1.25 ohms. So you can see that R equivalent is less than R minimum. So this is another important feature of a parallel combination. Let me mark parallel combination like this. So you can see that what happens in parallel combination, the number of resistors, if you are keeping on increasing, what will be the value of equivalent resistance? So the equivalent resistance will be less than the minimum resistance of the combination, where R minimum is what? Minimum, minimum resistance in parallel, minimum resistor, right? So that is the case. So you can easily now in competition exam, sometimes it is asked that these resistors are connected in parallel, then calculate the value of equivalent resistance. So sometimes you don't need to calculate anything, right? So in this MCQ pattern, they can ask in this way, right? So let us say this was your 10 ohm, right? And this was your 5 ohm, and this was your 2 ohm, right? This was your connected case, and this was connected to a 20 volts. So they will give you four options. Find the value of what is R equivalent. So they may give you four options. So one they will call as for 20 ohms. Second they will call as let us say 3 ohms. Then third case they will call it as 1.2 ohm, and D case let us they are calling as 30 ohms. So from this, sometimes what happens, you don't need to calculate the value of R equivalent resistance. You know this relation. You know this relation that R equivalent in parallel combination. First of all, this must be a parallel combination. In parallel combination, R equivalent is less than the minimum value of the individual resistance in this combination. So R minimum in this combination is 2 ohms. So obviously R equivalent is going to be less than 2 ohms. So in this option, this is eliminated, this is eliminated, this is eliminated. Only one left is this. So you can easily mark this, right? Now let us solve series combination is particularly easier, so I'm not going to, or you can consider a case of a series combination. Let us quickly consider a case of a series combination. Suppose these same three resistors are now connected in what series, right? These same three resistors are connected in now in series. So now you need to total find the value of I. Similarly, in this case, you know that the current is going to be the same in all the resistors, right? So V is nothing but equal to IR. Again, you can write directly V is equal I is equal to V by R equivalent. And R equivalent in a series combination, you know R1 plus R2 plus R3, which is equals to 2 plus 5 plus 10 and nothing but 17. right? So I, you can now find it as this one voltage we consider 20. So it is nothing but 20 by 17 amperes. So this is the total current 20 by 17 amperes which is flowing, which is equals to I1, which is equals to I2, which is equals to I, which is 20 by 17. And now again, similar for the series combination, you can see the value of R equivalent is what? 17 ohm, right? And what is the maximum value in this resistor case of series combination? 10 ohm. So you can see the equivalent resistance is 17 ohm. You can see that R equivalent is greater than the maximum value of the resistance in series combination, right? So this is another feature you can mark. So suppose in series combination so many resistors are given, then he is asking you to mark the correct value of the resistance, equivalent resistance. Then you can easily identify the maximum value of the resistance greater than that maximum value of individual resistance. The equivalent resistance is going to be that, roughly you can approximate. And sometimes the elimination method is helpful in calculating direct, right? So this is the case. Now let me consider the voltage difference, right? So V1 is nothing but IR1. So I is not 20 by 17. So I multiplied this by R1, which is 2. So this is nothing but 40 by 17. Similarly, V2 will be 20 by 17 into 5, which is 100 by 17. Similarly, V3 is what? 20 by 17 into your 10 ohms. So this is 200 by 17. So you can see that the larger the value of resistance, the directly proportional relation of the resistance you can see, because V is directly proportional to R in this case, in which series combination. Because I is going to be the same. You know that V is equals to IR, but I is same. It is same for all. So that is why V becomes directly proportional to R. So that is how you can see that the 10 ohm is the largest value of the resistor. So across that, largest potential difference is observed. And the minimum value of resistor is a 2 ohm. So across it, minimum value of voltage is observed. That is V is directly proportional to R in the case of a series combination. So that is another criteria which you can mark. Right. So these points you can remember in case of series and parallel combination. Now further moving to the series and parallel combination, sometimes what happens, tough combinations of these can be asked in the exams. Let us consider a very famous concept, famous kind of a question from this concept, right? So this is your point A and this is your point B. You need to find resistance RAB is what? That is the resistance between this A point and B point is what? So you can see that it becomes now a bit difficult to calculate series and parallel combination. Okay, you will see that okay, starting point for these resistors are same. Then it goes here, then this it becomes connected to the ending point, and then this ending is connected to this starting, and like this. So it becomes a bit difficult sometimes to analyze more complicated forms. So you need to what? You need to simplify sometimes this circuit. So you need to find resistance between A and B point, right? So what I do is a simpler method to find the resistance quickly is to redraw this circuit diagram. Suppose I mark this intermediate point as C and D. You need to find resistance between AB, that is fine. So I will try to redraw this circuit. Let us mark this point as A, let us mark this point as B. And in somewhere in space, I am going to mark the point as C and D. Now I will draw the resistances one by one. So between this point is A only, right? Same point, nothing is connected. So this is A only. So between A and C, you can see 3 ohm is connected. I will draw and mark 3 ohm like this. Now between A and D, you can see that 2 ohm is connected. Right? Mark the test. Now between C and B, it is connected as 3 ohms. 1, 3 and B. C and D, it is connected as 4 ohms. And between B and D also, you can see that between these 10 ohms is connected. So now your circuit becomes like this, right? Let me take this point as this as 2 ohm only, right? Because I want to tell you a more uh, one more concept here. So let me consider this as only, right? So this between C and B, let me let it be C and B, let it be 4 ohm only. Let us mark it as 2 ohm. Okay. Let us mark this resistance as 2 ohm. Right. This is 2 ohm. So between B and D, it becomes 2 ohm only. And between C and D, it is 4 ohm. Between C and D, it is 3. So this was your question. I have reduced like this. Now, since I have redrawn this circuit, it becomes like this. So this is your A point, B point, or you can mark it as this is also A point, B point, because nothing is. Now you need to find R A. Okay. Now let me tell one more thing from here. Right. You can see that if current is suppose entering from this point, let us say I is entering. Right. Then you can see that 3 ohm is here and 2 ohm is here, right? And again 3 ohm is here and 2 ohm of here. So suppose this is your R1, right? And this is your, let us say, R2. This is your R3 and this is your R. So you can see that R1 by R2, if I do, it will be equal to R3 by R. You can see that 3 by 2, R1 by R2. Here also 3 by 2. So this condition is satisfied. Since this condition is satisfied, you can see that when traveling, the resistance across these two currents will be here. Let us say I1 and I2 will be here, right? Now two currents will be flowing. And what will happen as the two currents are flowing, when this criteria is maintained, the potential difference between the C and D point, that is V, C, D, it is going to be zero. Right, this potential difference is going to be zero. That is potential difference, that is Vc minus Vd, you find it will be equal to zero. And what I told you, that for a current to flow there must be a closed path, that is fine, and there must be a potential difference. But what will happen in this case, there is not going to be a potential difference, there is not going to be a potential difference, so the current won't be flowing in this part, current won't be flowing in this part. So what will happen at this point, when this I1 will come, nothing will go here, and similarly this I1 will continue this path, and similarly this I2 will come here, and no current is coming from this part because I1 went straight from here, so I2 will continue here, and from here again I1 and this one I2 will combine and they will make IN. So that is the meaning. What happens? This is the spatial criteria of a circuit, and that is what we call it as Wheatstone bridge. So what we call this as? This we call it as Wheatstone bridge. So generally, what happens is this is the classical example of a Wheatstone bridge, because in this, for this combination to occur, you need at least 5 resistances. 1, 2, 3, 4, and 5 resistances are here. And this is the general pattern of a Wheatstone bridge, where you can directly see. Since this is a more complicated, drawn in a much complicated way, you can simplify like this, right? So this kind of a combination is there, then the current won't flow in this part. That is the meaning I want to explain is, this was your 3 ohm, this was again your 3 ohm, this was again your 2 ohm, and this was again your and in between these path there is a connected branch like. So you need to find the equivalent resistances. Now, since I want a current to flow like this, what will happen? Current will be flowing here and here, but no current will be flowing here. Right? No current will be flowing here means what? If the current is not going to be there, you can simply remove that branch. Because if current isn't flowing there, suppose V is equals to IR, right? Current isn't flowing there, it is zero. So what will be the value of V across here? It will be zero. That is the case, that is the first case only why I became zero. V is zero, that is why I became zero. So there is no drop observed. So simply you can redraw this circuit as like this. So this circuit now becomes like this. No current is flowing. This is I, this is I1, I2, and they will be. Now if you reduce this combination, how if you redraw this, what will be like? These 3 ohm and these 3 ohm are in series, right? And these 2 ohm and 2 ohm are in series. So you can redraw this as, this is nothing but now this one and this one. And that is, this part is now 3 plus 3, 6 ohm, and this one becomes 4 ohm. And this was your EN. So what will happen now? You can find the value of resistance. R equivalent is what? These are now parallel combination, right? These two are in series, and now this, after this series combination, this is now parallel combination. Again, you will find the value of equivalent resistance, which is 1 by R1 plus 1 by R2. So 1 by 6 plus 1 by 4. So you can calculate this. So you will be getting it as R equivalent, you will be getting as a 24 upon 10, which is 4.5. So this is how you are going to find the equivalent resistance. So this was the special combination of resistances which is known as the Wheatstone bridge. So this combination, it is the famous pattern is drawn like this. Rather, I gave you the question that was a complicated twisted form, so that you can also learn the technique how to redraw the circuit sometimes if you aren't able to see series and parallel combination. So this is an example of a Wheatstone. This is an example of Wheatstone bridge, and this is how it happens. There you can prove it also by using Kirchhoff's voltage law. You can prove this, that voltage across this branch is going to be zero, right? That is yeah, that is the current across this branch is going to be zero, right? Because what is the, why is the current zero here? If somebody asks, because the potential different, the volt electric potential at this point and the electric potential is this point is what? Same. So if the potential is going to be the same, there is not going to be electric potential difference. The difference is going to be zero, and that is the second condition for flowing of current is not maintained, and that is why you observe that no current is observed in this branch, right? So this is how you solve questions. Now there can be questions regarding some combinations such as series and parallel twisted or mixed in together. They can ask you to find the resistance. Suppose the question is like this, right? This is 2 ohm, this is going to be a 5 ohm, right? And then he is going to give you this R value, right? This is going to be the case, right? Suppose he gave the voltage across this this voltage across this particular 2 ohm resistance he is giving you as, let us say, 20 volts, right? So you need to find let us say you need to find this voltage also. Suppose this is V and the total current is I. So you need to find voltage, you need to find current, right? And you need to find the, let us say, uh, the value of R is given to you, and it is, let us say, 4. So now you need to find the value of I and V. So how you can find? Now you need find I also, V also. No, both are not given. So how you can find? You know that this is parallel combination here, right? So what, this is the 20-volt voltage across this 2 ohm resistance. So what will be the current in this 2 ohm resistor? It will be what? 20 by 2, which is equals to 10 ampere. right? So 10 ampere suppose is flowing here. This 10 ampere is flowing. And you know that these two are in parallel, so across 5 ohm also, the voltage is going to be V by R 5, V by R. So V is what here? 20 only because these are in parallel, and R is what? 5. So this is what? 4 amperes. Let's. So 10 ampere is like this, 4 ampere is like this. So what will happen? These two currents are meeting here. So this current will be what? Total I is equals to what? It's 10 ampere plus 4 ampere. So it is going to be 14 amperes. That is why how you find the value of this I, which is coming out to be 14 amperes. Now you need to find the value of voltage. Right. So one thing is for sure that it is going to be more than 20 volts because here 20 volt is already there. So voltage will be the sum of this 20 volt and the voltage drop across this R resistance. Right. So what you will do? You will now find the R equivalent. So R equivalent, how will you find? These two are in now parallel. So you can find as these 2 ohm, right? And this is 5 ohm. And this was your 4 ohm. You can see these two are in parallel. So these two in parallel will result in 1 by R1 plus 1 by R2, 1 by R equivalent. So you can find that this is 1 by 2 plus 1 by 5. So if you calculate this, R equivalent will be coming equal to 10 by 7 ohm. And now this 10 by 7 ohm is in series with this 4 ohm. So 10 by 7 and this 4 ohm and this 10 by 7. So 10 by 7 plus 4 ohm is the total R equivalent resistance, right? So what you will do? So 10 by 7 plus 4. So this is nothing but 28 plus 10 by 7, which is 38 by 7 ohm. So this is the total resistance, right? So what is now V? V is equals to I total into R equivalent. So what is I? I found it to be 14 ampere. So 14 into 38 by 7. What is this? 7 two times it will go. 2 8 just 16 and 76. So you can see that the total voltage is 76 volts. And you can now find the voltage across this branch also. How? You know that the voltage total, this total voltage is going to be V1 plus V2. You know the value of V1, it is 20 volts, right? 20 volts. These are in parallel. So this is nothing but between this point and this point, it is 20 volts, right? At 20 volts. So V is equal to what? 76 volt, 76 volt. You just now find. And V1 is what? 20 volts. And you want to find the voltage across that. This is V2 is what? 76 minus 20. So it will be what? 56. So that is how you can calculate each and everything. That is how the questions can be asked on this particular topic. Right. So different values. He can ask you value of resistance. He can ask you value of voltage. He can ask you the value of current. So this is how you can solve these questions. So this is about the series and parallel combination. More complicated questions can be seen, and we will consider some of the question at the end of the more question at the end of this chapter. So in the next class, we will be continuing about the power discussion of this power and heat discussion of this electric current. Because what will happen when electric current is going to flow in resistances, the electric current is going to flow. There will be some heat generated, and that we will be seeing in the next class, and we will also making some discussions on power and electricity bill and all that we will see in the next class.